Okay, so let's start. This is experiment number 6, which will be done in lab number 7. And as we've been discussing, that each one of these experiments involves design and then simulation and then prototyping in the lab. And one of the goals of this particular lecture is to illustrate that when design problems become complex, then it makes sense to take the complex problem and break it up into subproblems here, subproblem 1, 2, 3 here. The advantage is that the subproblems become simpler, easier to handle. And then they can also be allocated to different teams or different persons. And so one can share the labor of designing or solving that particular problem here. If the subproblem happens to be still complex, then it can be further broken down into even simpler problems here. So that's the methodology that we'll use in this particular lab here. All right, so this is what is called as hierarchical decomposition. So the objective in this particular experiment is to design a circuit which has the following characteristics here. This is the output voltage here and an input voltage here. So the idea is that given any input voltage, the output would follow this particular form here, the form that you see over here. You can see that is the behavior in this particular quadrant is basically the same in this particular quadrant here. And the motivation for building a circuit with this kind of a characteristics is as follows here. Now, in circuits, we need waveforms of various types. We need square waves, we need triangular waves, and we need sinusoidal also. And it so happens that the square wave and triangular waves are easy to generate. We have seen earlier that, for example, if you have a triangular wave, you can use a Schmidt trigger to convert a triangular into a square wave. And triangular waves are easy to generate. We can do that by having a current source which charges a capacitor and with a feedback mechanism. And triangular waves of variable frequency, the frequency can be easily altered by, for example, changing the charging current. And as you change the charging current, the rate at which the capacitor charges, that changes and that alters the time period here. So assuming that the triangular wave is easy to generate of variable frequency, then one way in which we can generate a sinusoid is to take the triangular wave, for example, the triangular wave that you see here, and shape it such that you get a sinusoid here. And so, for example, if I take a triangular wave that you see over here, and I pass it through my circuit which has this kind of a characteristics, V0 versus Vin, characteristics like this here, then for voltages up to 1.5, my output follows the input here. This is what happens here. Now from 1.5 to 3.5, you can see here the slope changes, slope becomes half here. So it doesn't follow a star curving here, and the slope becomes less here. Beyond 3.5 onwards, it becomes constant here. So what you see here is that the blue waveform that you see here is what you will get if you pass a triangular wave through this particular system here, through this particular circuit. The blue waveform is what you would get here. And in green, if you can see, the green shows the ideal sinusoidal waveform. So what you can note here is that if I take a triangular wave and I pass it through my circuit of this kind of a characteristics, I would get a waveform which approximates the sinusoid here. Now the approximation to the sinusoid can be made more accurate if in this V0 versus Vin characteristics I build in more segments here. This is composed of only 1, 2, and 3 segments here. And if I add more segments here, I can get a more gradual curve here rather than a piecewise linear here. And then the approximation will become more accurate. Even with this crude approximation that you see here, it can be shown that if I take a triangular wave, let's say from 0 to 4 amplitude, I get a waveform whose harmonic distortion is only 3%. So a perfect sinusoid, of course, will have 0 harmonic distortion. And our waveform, this green one that you see here, has an harmonic distortion of only 3%. But one thing that has to be kept in mind is that the circuit will work properly only if the amplitude is, let's say, 4 volt here. Because the breakpoints that you see here, 1.5 and 3.5, they've all been chosen for a particular amplitude of the triangular wave here. If the amplitude of the triangular wave changes, then the waveform that you get as an output doesn't resemble very well a sinusoid. For example, if I apply a triangular wave of 5 volt amplitude here, you can see that the red one shows the expected outcome from our circuit, and it's not as well approximating the sinusoid as was the case when the triangular wave input was 4 volt here. In this case, as expected, the harmonic distortion of our waveform is higher, which is 7.2% here. Alright, so our goal then is to design a circuit with this kind of a output versus input characteristics here. And again, as we discussed earlier, our methodology would be that this characteristics that we see is relatively complex. What we would do is the task of designing a circuit with this kind of a characteristics, we'll break it down into a simpler problems here. So we'll use this particular methodology here. So okay, so we need to design a circuit of this form, and if we note that the first quadrant and the third quadrant are basically same, so basically then if we are able to design a circuit which generates this part of the characteristics, then we should be easy to generate this part as well here. And if we note this part of the characteristics, we can see that we can generate it if we have 3 circuits. For example, a circuit which reproduces this part, and a circuit which is able to do this and this together, and if we add them up, then we should be able to get this complete characteristics here. And so, for example, if we have a circuit which generates the first part here, that is, for example, V0 versus Vin with the slope of 1, and this we recognize, of course, it's a simple wire, or for example, if it's needed, a buffer. The second part here that you see here, in this part we note that the slope is basically 0.5 here, and this part we can generate by if we have a circuit which gives us V0 versus Vin of this form here, where, for example, the output voltage is 0 up to 1.5 volts, and then after 1.5 volts it increases with the negative slope of minus 0.5 here. If we see that if we take this particular graph here and add it up to this particular graph here, then we note that after 1.5 we'll be able to get this part of the characteristics here. Okay, the slope of minus 0.5 and 1 will add up to give a slope of 0.5 in this particular region here. Similarly, if we have another circuit which is very similar to this one, except that it starts working after 3.5 volts here, and if we take this one and add it up to the sum of these two, then we'll be able to get this part of the characteristics here. So what we see is that this entire characteristics can be obtained by summing up circuits which perform this part plus this part plus this part here, and we note that basically then our task boils down to making a circuit which gives us this kind of a characteristics here. Okay, so the whole task of designing a circuit which gives us this complex characteristics can be finally broken down to designing a circuit which gives us this kind of a characteristics here. V0 versus Vn, where the output is 0 up to a point, up to a voltage, certain voltage, let's say B here, and after that the circuit starts giving us output, in this case negative, with the slope of, let's say, A. If we can find a circuit which gives us this kind of a characteristics here, then we can generate the entire V0 versus Vn characteristics that we see over here. Okay, now if we see this particular characteristics here, we note that there are two parts to it. One is, of course, that the circuit starts working after a certain, one may call a certain threshold voltage here, and the other part is that the circuit then has gives us a certain characteristics with a certain slope here. Now, so for the time being, let's ignore this fact that it has a certain threshold voltage. Let's look at a circuit which gives us this kind of a characteristics here. So which means that it has a threshold here, except that the threshold value is 0. And then after when V in becomes positive, then of course V0 starts following V in with a certain slope A here. And we note that if we can have a circuit which gives us this characteristics here, then maybe with some simple modifications we could obtain a circuit which gives us this kind of a characteristics here. Of course, the inversion is something simple here. Here we have V0 versus V in. V0 is positive, here V0 is negative. So inversion is fairly simple to obtain. And so that's one part. And then the other part is laterally shifting the graph here. So the graph here starts from origin here and shifting it right by a certain amount. So that's something that we'll have to see how we can do here. But so this is a simpler problem where V0 versus V in has a form of this kind. And the reason why we are doing it is we recognize that this one looks like a rectifier here, because note that for V in negative, we see that the output voltage is 0, and for V in positive, then V0, suppose the slope is equal to 1, then V0 will be practically equal to V in here. So this looks like a rectifier, and therefore we can try and build a circuit which gives us this kind of a characteristics by looking at rectifier circuits here. So a very simple rectifier circuit, of course, is you take a diode, half-wave rectifier here, diode in a resistor, and if we plot V0 versus V in, these are simulation results from Microcap. If we plot V0 versus V in, we see that the output voltage is very small. The diode starts conducting only when the input voltage becomes larger than a certain value, 0.6 or so. And so what we see here is that the output voltage is 0. And once about 0.5 or 0.6 volts, the input crosses that amount, then the diode starts conducting, and then practically the entire voltage that you see here gets dropped here. So the output starts rising, and the slope of this particular V0 versus V in is basically equal to 1 here. So it gives us a characteristics of this kind, except that we have it's already shifted towards the right by a certain amount, and it gives us a slope of 1 here. Now, if we look back to this characteristics, what we want is V0 versus V in, which not only starts from 0 here, but maybe starts from a arbitrary amount here. Okay, so for example, B could be 0.5, B could be 1.5 or 3.5. So we want this amount to be arbitrary. Further, the slope also we would like to adjust here. So in this case, we see here that the characteristic starts, the threshold here is close to the cut-in voltage of the diode here. If we want a larger cut-in voltage here, well, one option is, well, we can put two diodes in series here. And in this case now, instead of earlier starting from, let's say, 0.5 or 0.6 volt here, now it will start from about maybe 1.2 or so here. So by putting diodes in series, one could get threshold voltages which are multiples of diode cut-in voltage here. But the trouble with, but the slope here is still, slope is practically equal to 1 here. Because note that once the diodes turn on, then the voltage across the diodes remains reasonably constant, and then V0 basically starts following V in, and therefore the slope dV0 by dV in will be equal to practically 1 here. So we can't get slopes which are different from 1 here in this simple circuit. And the other problem with this circuit is that the threshold voltages are multiples of the cut-in voltage here. So we need a different solution where we can get arbitrary threshold voltage, say 0.8 or 0.9 or 2.8 arbitrary threshold voltages. And we also need different slopes here. So we're looking for a circuit, a modified circuit, which can provide us with these two features here. And so one way of obtaining it is by going to a circuit called precision rectifier. So in this rectifier, what we do is we use, it's still a rectifier, there is an R and then there's a diode, but we use an op-amp along with the R and the diode here. And if we look at this particular circuit here, what we find is that unlike a conventional rectifier circuit where the output voltage starts following the input voltage after the diode cut in voltage here, in this case, the output V0 starts following Vin right from 0 onwards here. Okay, so let's see how this particular circuit works. Now, when Vin is negative, the current of course flows in this direction here. And the current, then what happens is the diode turns on and the current flows through the diode here. The current flows through the diode and then through R here and into the source here. That's for Vin equal to negative. Now, once that happens, we note that this is an op-amp circuit and the feedback loop is completed through the diode here. And negative feedback loop is completed through the diode. And we know that an op-amp, an ideal op-amp with a negative feedback, we have a virtual ground property here. And therefore, the voltage at this particular node here, inverting input, will be close to 0 here. Because the non-inverting input is 0 here, so this will be 0 here, and therefore we'll get an output voltage V0 which is equal to 0 here. So for all negative voltages here that you see, the feedback loop is operating and the value, this is a virtual ground, and output voltage is 0 here. Alright, so this part we get here. Now the moment Vin becomes a little bit positive, now what happens is if it becomes a little bit positive here, note that the current is now going into the op-amp here. The current is going in here. And now, if we look at it, the diode, because the current is going in, this current cannot flow through the diode here. So the diode is open circuit. And because it is open circuit, the diode is open circuit, it means basically that we don't have any feedback loop here. So the feedback loop is not present. And therefore, you can remove this particular part of the circuit here. This is absent. And so this Vin, it wants to force the current in this particular direction, but the current has no path. The current can't flow through the diode here. And we know if it's an ideal op-amp, the current can't flow into the op-amp as well. And therefore, basically no current would flow. No current would flow. The op-amp is in an open loop condition here. And therefore, the voltage at this particular node will be simply equal to Vin because we have no path for the current. So this becomes Vin here, and this Vin of course goes to V0 here. So now we note that the moment Vin becomes positive, V0 becomes equal to Vin here. So we get a slope equal to 1 here. V0 starts following Vin here. And the output here, the op-amp, of course, because Vin is positive here, and so the voltage is positive here, so the op-amp is in the open loop condition, and the voltage here would be the negative saturation voltage here. So if we have plus minus 12 volt supply here, the output here is going to be close to minus 12 here. So the op-amp goes to saturation here, but V0 starts following Vin here. So we call it a precision rectifier because it can rectify very, very small voltages here. For example, if I have 100 millivolt sinusoid, then the 100 millivolt sinusoid will also get rectified here if you look at this particular characteristics here. Unlike a normal rectifier where you have to apply input voltages which are sufficiently large to turn on the diode here. This is not true because the diode is put in the feedback loop here. So use of a op-amp here and allows us to rectify very, very small voltages here, and we call this circuit a precision rectifier here. And the problem with this particular circuit is, as I mentioned, when Vin is negative, if you look at Vin negative, then of course the diode is on, feedback loop is operating, this point is 0, and the output voltage is 0.6 or 0.7. That's the diode voltage here. So this voltage is 0.6 or 0.7. Now when the feedback loop is not operating, when Vin goes positive here, then what happens is diode is open circuited. We said the value is minus 12 here. So when you apply a sinusoid here, what is happening is that the op-amp output is switching from, let's say, 0.7 to then going to us minus 12 here. So in a cycle, during the negative cycle, the op-amp is here, say 0.7, and during the positive cycle of the sinusoid, the op-amp is here, which is minus 11 or so here. So the op-amp has to switch from 0.7 to minus 12 here, and we know that op-amp, if you try to switch an op-amp, then there is a problem of slew rate here. There's a maximum rate at which the op-amp voltage can change, and therefore if we increase the frequency of the sinusoid, then the switching that you see here will not take place properly here because of the slew rate here. And its effect we can see, for example, if I apply a frequency of 0.1 kilohertz here, one can see that if you apply a sinusoid frequency of 0.1 kilohertz, so the idea is that this input is a sinusoid with frequency of 100 hertz here, and we are looking at what happens to, let's say, V0, what happens to the output voltage here. Okay, so we see that the output gets nicely rectified here, no problem. And this is the op-amp output here. We see the op-amp, is able to make a transition from -11 to 0.7 or so nicely because the frequencies are low, and so the op-amps and they are working fine here. Let's increase the frequency, and the transfer characteristics V0 versus Vin looks fine here. Let's increase the frequency to 1 kilohertz. We can begin to see some problem here. It's no longer if you look at the output, it's no longer rectifying as well. We can see a small negative portion here, which we don't want. And the op-amp output we can see here is not following, is no longer as abrupt as we would have wanted here. And if we increase the frequency to 10 kilohertz, we can see now severe distortions here. Rectification is not occurring as well. We have a significant component which is negative in the output voltage here. You can clearly see the slew rate effects here. The op-amp output is increasing linearly, and this is basically what is causing this particular distortion here. And if we plot V0 versus Vin here, you can see it's no longer a proper rectifier with a lot of distortion here. So all these problems are arising because in this particular circuit, what is happening is when Vin is positive, the op-amp is in open loop condition, and when Vin is negative, the op-amp is in closed loop condition here, and this is causing the output to make a large transition from 0.7 to -11 here. Now, and so this is causing slew rate problems, and this would prevent our circuit from working at higher frequencies here. So one way of avoiding this problem is by ensuring that even when Vin is positive, the op-amp doesn't go in open loop condition, but it is in a closed loop condition here. And ensuring that the transition that the op-amp output has to make, the transition in voltage between positive and negative cycles of the sinusoid are small, and therefore the slew rate effects are minimized here. So this can be done through this new circuit that you see over here. Okay, in this case, let's see how this particular circuit works here. So when Vin is positive, then of course we would like current to flow. In this direction here into the op-amp here. Now if we look at this current goes through R1. It can't flow through D1. So D1 is open circuit here. So what the current does is goes up, flows through R2 here, comes into the diode, and then flows into the op-amp here. So we have a closed loop here, and it's easy to show that V0 will be equal to Vin R2 by R1 with a negative sign here. So it acts like a normal inverting amplifier, except that there's a diode also in the path here. So D1 is off, D2 is on here, and then the V0 is basically equal to Vin minus R1 by R2 here. And the op-amp output at this particular point would be whatever is the value of V0. You subtract the diode voltage here, 0.7 or so. So that would be the op-amp output here. So if I have Vin, let's say, if I have a sinusoid of voltage, let's say 1 volt sinusoid here, then and let's say the gain of the circuit R1 by R2 is 1 here. So so the maximum value of V0 then is about 1 volt here, and the value of this op-amp output would be 1 volt minus, let's say, 0.6, about 0.4 here. So in the positive cycle, the op-amp is, say, about 0.4 here. In the negative cycle, what happens is when you make it negative, then the current has to come out like this here. And in this case, we note that the path of the current would be through D1 here. So D1 turns on here, and because D1 turns on, and note that current can't flow through this particular path here. So this particular path is open here. The path through D2 is open here, and the path through D1 now is active. And again, there is a negative feedback. So what happens is there is virtual ground here, and the virtual ground ensures that this value is basically equal to 0. So if this is 0 here, then we note that there is no current flowing through R2 here. So if this is 0, no current is flowing through R2. So the value of output voltage is basically equal to 0 here. So when Vin is positive, then we note that V0 is basically equal to 0 here. V0 will, when Vin is negative here, D1 is active and V0 is basically equal to 0 here. So we note that, and in this case, we note that the op-amp output is about 0.7 here. So in both for positive cycle as well as negative cycle here, the op-amp output is now really limited. It doesn't go very high. It doesn't go to a saturation because the feedback paths are active in both positive and negative cycles here. And the transition that the output has to make as we go from positive to negative cycle is really small, just limited to 1 or 2 volts here as compared to maybe 10 volts here. So slew rates are minimized, and then the circuit is expected to work at higher frequency here. So this is the characteristics at 100 Hertz. Seems to work fine. At 10 kilohertz also note that the characteristics are reasonable here. The characteristics, there is no distortion here. You can see in this particular one here as compared to the previous circuit here. Alright, so what we have been able to do is get a circuit which gives us a V0 which is 0 here for negative Vin, and then it begins to follow with a certain slope here. And the slope we can adjust by simply adjusting the ratio of these two resistors here. So in this case we have the gain is 2k by 1k, the gain is 2, so the slope is equal to -2 here. If we make, instead of 2k, we use 1k, the slope will become equal to 1, and therefore one can adjust the slope that we want here. So one additional problem. One additional problem that we have to solve is that we've got the slope, any arbitrary slope that we want. We would like to shift this graph to the right by an arbitrary amount here. So one way that we could, and of course before we do that, we note that we got this characteristics, and if we reverse the polarities of the diode here, D1 and D2, we can get the complementary characteristics here, where V0 is 0 for positive Vin, and then for negative Vin, it follows the Vin with a certain slope here. Alright, so that's easy to get. Alright, so the issue then is, how do we shift the graph to us along the x-axis here? And one way that we can do is, for example, we can, instead of having a ground here, we can attach a voltage here. Alright, so if we attach a voltage at this particular point here, note that then this raises the value of this particular node here, and therefore it would raise the value of V0 over here. Okay, so for example, if I add a voltage of 2.5 volt here, so then note what will happen is the characteristics that you see here, earlier characteristics note was from here, the blue one starts from 0 and has a certain slope. Now what happens is it starts from close to 2.5 here. 2.5 here, so we are able to shift it right, but then what happens is, note that the characteristics get shifted up as well, because we added voltage at this particular node, so the characteristics, apart from shifting towards the right here, it gets shifted up also. So that's something that we don't really want here. Another alternative is that what you do is you put an additional source here, a bias here, along with the resistor. So in this case, note that what would happen is that earlier we were saying that when Vin is positive, this particular path is active here through D2. This particular path is active through D2, and V0 was basically following Vin with a certain slope here. But now that we have put -1 here, for example, this particular path, remember, will be active when the current has to flow like this here. But then this -1 requires a current in this direction here. So this particular path will become active. This path will become active only when V in by 1K becomes larger than the current that is required here. All right. So when this current becomes larger than the current required here, then only a current would start flowing in this particular path here, and then V0 will start following V in here. So in effect, what would happen is, if you analyze this, what would happen is that only when V in is larger than 1 volt will this path become active, and V0 will start following V in. And for V in less than 1 volt here, then this particular path will be active here, because minus 1 volt, remember, we have basically negative feedback either through D1 and D2 valid in both positive and negative cycles here. So this point is virtual ground throughout. So if this is virtual ground, then we need a current of 1 milliamperes that is flowing over here. So it either has to come through D1 or it has to come through D2. So when V in is less than 1 volt, then this cannot supply this current here, and the current then has to come through D1. And when it comes through D1 here, the path D2 becomes inactive and V0 is 0 here. So by adjusting the value of resistor here and the bias voltage here, we can easily shift the graph here. So in this case, for example, when we put 1 volt here, we can shift the curve to the right by about 1 volt here. In fact, precisely 1 volt here. So then we've been able to, we said that if we want to generate a characteristics of this kind here, we need circuits to generate these waveforms here, and they basically required, so the problem basically boiled down to generating or designing a circuit with this kind of a characteristics, and that's something that we can do here. So now all that we have to do is design a circuit which gives us this kind of a characteristics, another one which gives us this here, and this, as we said, is simply a wire here, and then add them up, and then we should be able to get this kind of a characteristics here. Okay. And since we have to add up these different characteristics, this is a well-known op-amp summer a circuit which is able to sum up different voltages. So this can be useful for our purpose of generating the final voltage here. All right, so this is so what we are doing in this part here is just illustrating a circuit which will do this part here in the red. So only the first quadrant. So one can see here. So we have a circuit that you see here, this part. Note that we have put a voltage of minus 1.5 here. So what this part of the circuit does, and there is a slope of, note that 1K and 1K, so there's a slope of 1. So this part of the circuit is basically has this characteristics here, V0, V in, 1.5, which is determined by voltage here. Slope is equal to minus 1. The slope is 1K by 1K here. So this part of the circuit here. Then we have this part of the circuit here that you see here is similar, except that it starts from 3.5, and it also has a slope of minus 1 here. All right, so this is this here. And then we have simply a wire that you see here, wire here. And now what we are doing is we are summing up. So we've used if you note, we've used 2K here and 1K here. So this 2K and 1K will give a slope of or a gain of half here. So the gain of half multiplied by minus 1, so that will give us minus 0.5 here. Similarly, we've used 2K here and 1K here, so that gives us a gain of minus half here. So that will also give us 0.5. This is what we wanted here, and 1K and 1K, so this is simply like a gain of 1 here. And so we add them up, and we should get the characteristics that we want here. Except that, so we'll except that what happens is, note that this gives us this characteristics here and here, and then it goes through another inversion. So what we end up getting is the characteristics of this kind here. Okay, characteristics that you see here. These are, of course, simulation results, and with some changes we could have gotten the easily the characteristics in the other quadrant as well here. And so for example, these are simulation results. If I apply a triangular wave of 4 volts here to my circuit, and you can see the output looks, the red one shows the perfect sinusoid, and you can see the output follows the sinusoid pretty well here. This shows it more clearly. This is the output. The blue one shows the output of our circuit here when it's excited with a 4 volt triangular. When I give a 5 volt triangular wave, as expected, the circuit will not work very well. The approximation to the sinusoid is poor in this case. Okay, so so by following an approach like this, by using circuit blocks of this particular kind here with appropriate threshold voltages and with appropriate gain, and then by summing it up, we should be able to generate any piecewise linear characteristics of this particular form here. Now, in the lab, what we would like you to do is generate only the characteristics in only one quadrant here first, and then if time remains, then you can generate the characteristics in the second quadrant as well, and then test it out with a triangular wave of 4 volt amplitude. And these are some of the experimental results there, which just shows that the concept that we have outlined works reasonably well here. So this is our standard precision rectifier circuit here. You can see it rectifies quite well. These are experimental captured from the oscilloscope here. These are the V0 versus Vin characteristics here. Note that these characteristics work well when the frequency is low. When we raise the frequency 25 kilohertz, then the characteristics get highly distorted here. This is the complete circuit for one half here. Actually, we were required to generate, in this half, in the first quadrant, and in this case, what we have is in the fourth quadrant here. But note that all that we have to do is add an inverter, and therefore invert this, and therefore we'll get this in this half here. So that's trivial. You can clearly see all the segments here. The first segment with the slope of 1, then a slope of 0.5, and then something which is flat here. And when this when the circuit was excited with the triangular wave that you see here, this is the output of the of our circuit here. Okay. So you can see that seems to is not a very good approximation to a sinusoid, but is beginning to look like a sinusoid here. And as we said, that if you add more segments here instead of a 3-segment kind of a thing, let's say if you add if you double it, add 6 segments here, then of course the approximation to a sinusoid would become more accurate here. Okay. Again, as we have said, the circuit would work for a particular value of triangular wave input here, in this case 4 volt. If you increase the amplitude of the triangular wave, let's say 6 volt here, you can see the approximation becomes a poor. Approximation to the sinusoid becomes poor here. Alright, one last thing is when you make this particular circuit, you'll require several op amps. For one half of the circuit, you'll require maybe 3 op amps, and for the whole circuit, you'll require 6 op amps. And it's best not to make circuits like this here. What you should do is you should plan your layout properly so that the circuit is easy to understand, easy to debug. And if you have all these wires coming from here from all directions, it's going to become, if there's some wrong connection or if there's something not working, it becomes difficult to modify. So the goal of, while you're making circuits on the breadboard, the layout is important. Where you run the power line, where you run the ground line, where you take the outputs is important. And so spend some time, besides designing the circuit and simulating it, spend some time, give some thought to how you're going to lay out your circuit here. And try to make it as neat as possible. This would help you to debug and complete the experiment in the time allocated. Okay then, so let's, as I said, this is a useful circuit and a fairly easy circuit, easy and interesting circuit here. All right.